Hi, I'm Dave Brown for Teletrain, and today we'll be discussing air preparation, Lesson 11 of Parker Hannafin's course on industrial pneumatic technology. The pneumatic components and systems we have been discussing up to this point require compressed air that is free of contamination, because no matter how well a system is designed, if contaminated air gets into the components, it can interfere with proper circuit operation. Today we're going to cover the types of contaminants that can be found in the air used in pneumatic systems and ways that are used to clean it up. First, contaminants in a pneumatic system come from three basic sources. They may be built in, generated, and ingested. Let's see what these terms mean. The first is built-in dirt. It can occur in newly fabricated systems when good installation practices aren't followed. Valves, tanks, even the piping itself can become a collector for rust, paint chips, dust, sealant tape, even cigarette butts. In fact, many harmful dirt particles are invisible to the human eye and cannot be removed by wiping with a rag or blowing off with an air hose. The second source of contamination is dirt generated within the system during use, like this rust. Or as a system operates, moving parts begin to wear and often generate small wear particles. When these flakes become loose, they get carried downstream by air pressure and can jam valves or damage pneumatic tools that might be used in the system. The third source of contaminants are those added to the system, that is, ingested. Here's a good example. A mechanic repairing a valve in a dirty environment. Unless he's very careful, it's quite likely that some of the grit will end up inside the valve before he's done. Dirt can also be added to a system through a cylinder. When the cylinder rod wiper wears so the outer sealing edge isn't able to wipe off the fine particles of dirt, they can be drawn into the system as the cylinder is stroked. The contaminants that can get into a system are divided into three main groups. They can be abrasive or hard dirt, soft dirt, and entrained liquids. Hard dirt may come from inside or outside the plant. A couple of the best examples are foundry sand and grinding wheel residue. If hard dirt gets into your system, it can cause faulty operation or premature component failure. Here are some examples of soft dirt. They include soft dust, like this, particles of dried paint, even certain types of pipe joint compound. Once it gets into a system, soft dirt can plug orifices or cake around valve or cylinder ports. If this happens and airflow is reduced, the components may not work and the system may not function properly. The problems you see here, a rusty pipe, and this seal that has deteriorated and swelled up, were both caused by the same type of contamination, entrained liquid. Entrained liquids are liquids that enter the system along with the air. Probably the best example is water. It's present as moisture vapor and can get drawn in through the air intake. It can cause the rust and seal damage we have just seen. Okay, so we know that there are three types of contaminants, and we've seen the damage they can cause. How do we know if they are in the system? Can we see all of the particles? Well, the answer is no. Although some contaminants can be seen, many of the harmful particles are too small for us to see with the naked eye. And to understand that, we should know how contaminants are measured. The unit of measure is the micrometer, which is also referred to as a micron. And it equals 1/millionth of a meter. That is 1/millionth of the length of the rod that is being held here. 1 micrometer is equal to 39 millionths of an inch. So a micrometer is very small. 1 grain of table salt measures 100 micrometers. This human hair here, about 70 micrometers. And many of the particles in the air in a pneumatic system are even smaller than this. So you'll find devices like these used in most pneumatic systems. They are all filters, and their purpose is to help remove contaminants from the air in our system. Remember back in Lesson 5, we said that the first line of defense for industrial compressed air is the compressor intake filter and the aftercooler. Well, the last phase of air preparation takes place at the individual pieces of equipment that are supplied by the air system. An airline filter is a device that is placed in the airline at the workstation to be protected. Its purpose is to remove contaminants from the air that passes through it. On a pneumatic circuit diagram, the filter is represented by this symbol. An airline filter basically consists of a housing here with inlet and outlet ports. Here is a deflector plate and shroud, and here is the actual filter element. Also, we have a baffle plate here and a drain at the bottom of the bowl. Let's see how this unit works. The inlet directs the incoming air through the openings in the deflector plate. This causes a swirling action that throws the larger impurities and condensation out by centrifugal action. They collect on the sides of the bowl and run down past this baffle here into this quiet chamber where they can be drained off through the bowl drain. The air then reaches the filter element. In this second stage of filtration, any smaller particles that are still airborne are filtered out and trapped by the filter element. The filtered air then passes through the outlet here to the workstation. You can see that the filter element has an important job to do. Filter elements are generally divided into 2 types: depth type and edge type. With the depth type element, air is forced to pass through an appreciable thickness of material. Dirt is trapped as the air moves through the small openings in the filter material. Here are some typical depth type elements. This one here is constructed from porous bronze, and although you can't see them, there are actually paths through it to allow air to flow. This one is made of foam plastic and works the same way. This is what an edge type filter element looks like. Air has a pretty straight path through the filter, but dirt being carried by the air is caught and trapped on the edge of the element here that faces the airflow. Here is a typical edge type filter element. It is constructed from resin-impregnated paper ribbon. You'll find that filter elements are made from many different materials, such as cloth, felt, wire mesh, even ceramic. Some are throwaway types, while others are designed to be cleaned and reused. And when you are replacing air filter elements, make sure you replace them with the kind specified for the unit. It's always a good practice to check on the element rating. Because of its construction, an airline filter may have many pores of different sizes, many of them small, some of them relatively large. If the element has no consistent hole or pore size, a filter is given a nominal rating. The rating is established by the manufacturer and indicates the expected average hole size in the element. For example, a depth type element with a nominal rating of 40 micrometers indicates that the majority of the pores in the element are 40 micrometers in size, and that a large percentage of the 40 micrometer particles will be trapped. Filter elements, like those we've just described, will do a good job of removing hard and soft dirts, and most of the entrained liquids. But if you need air that is almost completely free of contaminants, you'll have to use one of these, an oil removal filter. They come in many different sizes and shapes, but they are all designed to deliver very clean, oil-free air to the workstation. Oil removal filtration is needed in many different applications, such as dental and medical, pharmaceutical, food processing, and paint spraying, just to name a few. These filters can be very efficient. One of these units, equipped with a pre-filter, can remove as much as 99.9% of the oil and particles down to approximately 0.3 micrometers. Let's see how it's made and how it works. Note that an arrow indicates the direction of air flow. Contaminated air enters here and is directed to the interior of the filter element. Since it is under pressure, it is forced through the filter element, which is a membrane made from borosilicate glass fibers, sometimes coated with epoxy. As the air passes through the glass fibers, very small oil and water particles are coalesced to form liquid droplets. These fall to the filter sump, where they are periodically drained off. Okay, so we've collected the liquid and particles in the bottom of the filter, and we've got to drain them off. Basically, it can be done two ways, manually or automatically. If a manual drain is used, maintenance personnel must check the filter regularly and open the drain if the contaminant level is too high. Some manual units have a petcock like this. Others use a spring-loaded design like this. The second type of drain is the automatic drain. It's a device placed in the quiet zone here at the bottom of the filter. Typically, it has a float, and when the float is raised, a port is opened, allowing the liquid and contaminants to discharge. Well, we've talked about filter operation and the different types of filter elements. Let's briefly examine the bowls themselves. Depending on the manufacturer and the filter application, bowls can be made from different materials. This one is made from aluminum. This one is perhaps the most common. It's made from a material called polycarbonate. Polycarbonate is a good material for bowls because it is transparent and tough. It is suitable for use in most industrial environments, but it shouldn't be used where it can be subject to high impact blows or to temperatures outside of the rated range. This bowl illustrates another point. As with most plastics, exposure to certain chemicals, generally any type of solvent, can cause damage. So before you install a polycarbonate bowl and place it in operation, check to see what cautions or special directions are provided by the manufacturer. Although metal bowls will resist the action of most solvents, strong acids or bases, even salt-laden atmospheres, can damage them severely. It is also common practice to protect polycarbonate bowls from mechanical damage that might be caused by a sudden blow. Two types of bowl guards you may see are this one here, which is made of metal, and this one here. It's made of polyethylene. As you can see, the guards do a very nice job of protecting the bowl from damage. When you are replacing an airline filter, make sure you replace it with one of the same flow capacity. Sized too small, the result will be a high initial pressure drop at the rated flow, and this can cause possible air starvation downstream. If you replace one with a filter that is too large, you can get a low swirling velocity inside the filter, and this means that contaminants won't separate out well. The device you see here helps to ensure trouble-free operation of pneumatic system components. It's an airline lubricator. Except in those systems designed for oil-free air, pneumatic components like cylinders, motors, and air tools must be lubricated if they are to work properly. So the lubricator actually puts oil into the air that feeds them. And when the air reaches the equipment, it spreads a lubricating film over all exposed surfaces, like cylinder walls and seals. Lubricators are of three basic types: injection, standard mist, and recirculating mist. Drops of oil are sometimes injected into an airline by what is called an injection or pulse-type lubricator. A minute amount of oil is delivered directly into the pneumatic component, and the oil injection is proportional to the cycle rate of the unit being lubricated. A more popular method of lubricating is to spray the oil into the flowing airstream in such a way that it forms a mist. Most standard airline mist lubricators, like this one, can deliver oil particles ranging in size from 1/100th to 500 micrometers in diameter. This is the inlet port here. Here is the outlet. And this screw is used to adjust the oil feed rate. Air entering the lubricator is channeled in one or two directions, depending on the rate of flow. At low flow rates, the majority of the air flows through this venturi section here, where it creates a low pressure area. Since pressure is then higher in the bowl, oil is forced up this pickup tube and past this metering adjustment. Drops of oil drip into the venturi section here, where they are broken into fine particles, mixed with the air, and carried to the outlet. At higher flow rates, this little rubber baffle bends down, so excess air bypasses the venturi section and blends with the venturi-produced oil-laden air at the lubricator output. Some lubricators do not have a blowback check valve built into them to prevent reverse flow from the bowl chamber. Therefore, it is good practice always to shut off the pressure before filling a lubricator. When an extremely fine mist is required, a system may use this type of lubricator. It is called a recirculating mist lubricator. And you can see that on the outside, it doesn't look much different from the standard mist type we just covered. The big difference is that it can deliver oil particles ranging in size from 1/100th to 2 micrometers in diameter. One advantage of this kind of unit is that the smaller droplets will stay in suspension over a greater distance or for a longer time, so you can have a longer run from the lubricator to the work point. The recirculating mist type works much the same as the standard mist lubricator. Venturi action draws oil up from the bowl and mists it into the downstream air. The difference occurs here, after the oil-air mixture leaves the venturi. When it leaves the venturi, the atomized oil is deflected against the inside wall of the reservoir here. This action causes larger oil particles to coalesce out, and they fall back into the reservoir where the oil can be recirculated through the lubricator again. The very small oil particles keep right on going to the point of work. Here's an important point to remember. A recirculating mist type of lubricator can be filled only when the supply pressure is shut off. If it isn't, you can have a real mess on your hands or in your face. Just as with filters, lubricators come in many different sizes and shapes. The selection depends largely upon the airflow rate, and the system designer should take into account the pressure drops across the lubricator when it is delivering rated airflow. Okay, we've said lubrication is necessary to coat resilient seals, reduce friction, and extend the life of system components. However, just because a little oil is good does not mean a lot of oil is better. Many times, lubricators are adjusted so that too much oil is injected into the airstream. When this happens, puddles of oil can actually develop in the piping and cause problems. More importantly, however, exhausting air that has large amounts of entrained oil may carry enough airborne particles so that the air in work areas may not meet federal standards. This is so important that OSHA regulations state that air must not contain more than 5 milligrams of oil mist particles per cubic meter of air. That means that the amount of oil in the air in a plant of 200,000 cubic feet, and that's equivalent to a building 100 feet by 200 feet and 10 feet high, exceeds the 1 ounce we've placed in this cup, the air won't meet federal regulations. Therefore, be careful not to over-lubricate the system. Even when you're careful, many plants which use pneumatic systems still find it necessary to remove the oil from the system air with an oil removal filter before it is exhausted into the atmosphere. Many applications require filtration, regulation, and lubrication all at the same workstation. Therefore, most manufacturers combine these functions into a single pre-piped unit called an FRL unit. The FRL stands for filter, regulator, lubricator. And as you can see, because the components are made into a pre-piped package, they make for easy installation. Here is how an FRL unit would look in a circuit diagram. Here is the symbol for the air filter. Here is the regulator. It is pilot operated with a gauge indicator. And here is the symbol for the lubricator. Sometimes you'll see this symbol used for an FRL. Here are some tips when you're using FRL units. First, make sure they are sized properly and will provide the maximum required flow rate for the part of the circuit they are supplying. They should be placed as close as possible to the point of work and accessible so you can easily perform periodic maintenance tasks such as filling, adjusting, and cleaning. And whenever possible, locate a lubricator at an elevation that is higher than or equal to the height of the unit being lubricated. This concludes Lesson 11 of Parker Hannafin's course, Industrial Pneumatic Technology. The exercises for this chapter begin on page 145 of your text. I'm Dave Brown for Teletrain.